All right, in the last video, we introduced the concept of entropy, we introduced the concept of spontaneity, whether a reaction is spontaneous or not. Let's talk a little more about entropy. We kind of got started on that and didn't really finish it. So, entropy is delta S. Okay, we've seen delta H, we've seen other things like that. This is delta S. I don't know why entropy is delta S, but I also don't know why enthalpy was delta H. Neither of those seem to make sense to me, but that's okay. So we're going to define entropy as Q reversible divided by temperature. So what this really means for us is this is the heat exchanged in a reversible manner at a given temperature. In Kelvin. Okay, that sounds a little weird. Heat being released or absorbed is what we've been visualizing as delta H. So it's basically how much energy is exchanged, and the reaction has to be entirely reversible, okay, which delta H did not have that requirement. And it is temperature dependent, which is why we're dividing by temperature here. So at any given temperature, delta H is going to be a little bit different. Okay, that's okay. This is similar, similar to delta H in the sense that it behaves just like it did for like Hess's law. So what I mean by that is if you have multiple reactions, you can add them together in the same way that we could add delta H values and everything canceled out. You could also, if you reverse an equation, the sign of delta S will change. If you double everything, the sign of delta S will, the value of delta S will double. Same stuff that we saw for delta H. Okay. One way to calculate entropy is to do something called standard molar entropy. It's really similar to something we saw for delta H, but that's okay. It's abbreviated as an S with this little degree sign. This degree sign just means that it's happening at standard conditions. Okay, so this is the entropy of 1 mole of material, so whatever the reaction is, 1 mole of that, at 25 degrees Celsius and at 1 atmosphere of pressure. So basically standard conditions. So 1 mole, this is room temperature, and this is 1 atmosphere, okay? And we can use it to calculate delta S. Okay, delta S at standard conditions for a reaction. The one thing that's going to be slightly complicated about delta S compared to delta H is delta H was always kilojoules per mole. Delta S, or S, is always joules per mole Kelvin. Okay, so the units are in joules per mole instead of kilojoules per mole. I'm not entirely sure why that is. Honestly, I think it would have made more sense to keep everything in kilojoules, but that's okay. So, this isn't real difficult. Essentially, the summary of the entire concept is it's just products minus reactants. Okay, it's going to be a common reactants. This is going to be a common reoccurring theme for the next couple chapters. Is anytime we have like this balanced equation thing, we're going to take products minus reactants. So, I'm going to write it in the complicated version. Okay. It is the sum, that's a uppercase sigma, of the coefficients of the products times each of their individual values of the products minus the sum of the coefficients of the reactants, that's what's supposed to be an R, of the reactants times their S values for the reactants. So we label this as these things mean the coefficients. Honestly, all it is you just look up all the products and you look up all the reactants. You take them times you look up their S values and you take them times the coefficients. For most textbooks, this is Appendix C. I will give you any of these values that you would need for quizzes or exams. I do not need you to memorize Appendix C. Okay, but let's try an example. I will also be posting Appendix C on course so that you guys have a variation of this to look at. So let's just try an example. So let's say we've got this reaction. For HCl gas, the state symbols will matter a lot for looking these things up. So please pay attention to that. And the reaction goes to form, or 4HCl plus O2 forms 2Cl2 gas plus 2H2O gas. At first glance, we can see that our number of moles of gas is going from 5 on this side to 4 on this side, which means we should expect the entropy to actually be decreasing for this reaction. We'll see what happens, but we're actually going to look up all the numbers and do it right. But literally what you would do is, this is a photocopied table of Appendix C out of a textbook. I can't guarantee this is the one I'm going to post on course, but it's the idea. It's divided by element, so here's a bunch of aluminum compounds, here's a bunch of barium compounds, here's a bunch of carbon compounds, so on and so forth. And there's a column of delta H values, delta G values, which we'll deal with later, and S values. You'll notice that delta H and delta G are both in kilojoules, just S is in terms of joules per mole per Kelvin, okay? But literally, you just look all these things up. So for HCl, for this particular, honestly, I have the values already. I'm just gonna show you the concept. So basically, if you had, here, let's just look at a random example. If you had something like calcium bromide, the S value for this would be 130 joules per mole Kelvin, and you would just look it up, and if it was, if there was a 3 in the front, you would take it times 3. But literally, all we're gonna do is we're just gonna take the products minus the reactants. So, delta S for this reaction would be 2 times whatever the S value is for chlorine, plus 2 times whatever the S value is for water, minus the reactants. So minus 4 times the S value for HCl, and minus 1 times the S value for O2. Okay, products, which are these two, minus reactants, which are these two. If you look them all up on the table, which I'm going to be lazy and just give you the numbers, this value comes out to 223 joules per mole per Kelvin. So it's 2 times 223.0 joules per mole Kelvin. Okay, plus 2 times, this value is 188.8 joules per mole Kelvin, minus 4 times, this value was 186.7 joules per mole Kelvin, minus this value was 205.0 joules per mole Kelvin. Handwriting's getting sloppy there, sorry. Anyway, and literally you just add up all the products minus the reactants. And delta S for this reaction at standard conditions, the little degree sign means standard conditions, comes out to be negative 128.8 joules per mole Kelvin. Okay, so this has a negative delta S, or a negative sign, but it's a negative delta S value, which agrees with what we said at the beginning. We said that in general, the entropy increases if you increase the number of moles of gas. Well, this one's going from 5 to 4, so it agrees with the idea that the number of moles of gas is decreasing. So, again, not a huge deal. We're just, for right now, just trying to figure out how to calculate it. But literally, it's just the sum of the products minus the sum of the reactants times each of the individual coefficients along the way. I will give you the delta, or the Appendix C values. I do not need you to memorize those. Okay, so not a huge deal, but that is little more detail on delta S. All right, thank you.